topic of apparent weight. We have talked about this before, certainly part of the grade 11 course when we did normal force, because apparent weight is really normal force is the short answer. But some things just to keep in mind, that mass is unchanging. So whatever your mass is, no matter where you are in the universe, it's the same. However, weight does change depending on where you are in the universe, because we know that weight is force of gravity, right? So on the surface of the Earth, it's your mass times 9.8. But if you're on Mars, where the gravitational field constant is 3.7, excuse me, then you'd only have a weight of 241 newtons. So weight is not the same as mass, and weight changes no matter where you are. If you were outside of a gravitational field in the middle of the universe somewhere, you would have 0, right? And then there's the idea of apparent weight. Please pause if you need to keep writing. I'm just going to move ahead here. Apparent weight is standing on a scale. It's how heavy you feel, right? So we did this and we rode the elevator in grade 11 physics, right? It's what's pushing up on you. And when you're on say the Leviathan at Wonderland there, and not that I've ever experienced this on that ride anyway, and I never will, but you're dropping down that first hill. It's almost like you have no weight. You feel weightless, right? That's because there's no normal force acting on you. Like the ground's dropping out from beneath you, right? And then you hit the bottom, and you feel really heavy. That's because the roller coaster's changing speeds to move up, and you're kind of still moving down, right? And so you have a huge normal force. And that's a huge G-force impact. So apparent weight is the best way to understand apparent weight is sort of if you're standing on a scale, what it would read. Okay. So just looking at an example, weightlessness means you have an apparent weight of 0. So for example, you're in free fall, falling out of the Leviathan in a freak accident. Your mass is still your mass, but it feels like you're weightless, and that's because and you still do have a weight. You still do have a weight of your mass times 9.8, but you don't feel like you do, and that's actually the the Chris Hadfield videos, if you ever watched any of them, or you should watch some of them, and this idea of being the ISS and they're weightless, right? Well, this is sort of something I was hoping we could talk about a little bit in class, but the idea of, we know that the ISS is within Earth's gravitational field, so why would you feel weightless? It doesn't make any sense. Anyways, we'll talk about that. So looking at a quick example, oh, sorry, I just gotta fix this. This always happens. So I can't see my example, but this is very similar to some of the questions you did with normal force in grade 11, and certainly similar to your experience when we went on the did the elevator thing standing on a scale, right? Sorry. Okay, so on an elevator, you're moving upward with a acceleration of 1.5 meters per second squared. That's supposed to be squared, and then it moves with constant velocity. And as it approaches its stopping point, it undergoes a downward acceleration. It's slowing down, moving up, right? We want to calculate the apparent weight of a passenger with 75 kilograms under the 3 situations. So let's call up positive. So when I say positive acceleration, it means you're accelerating up. Okay. Just looking at, for part A, a free body diagram. And we're looking at apparent weight. So what am I really calculating? Normal force. Okay. So apparent weight is normal force. So we know the acceleration. So these should be very easy questions. I just wanted to take the time to do them in this class, sort of using the language of apparent weight. Okay. Mass times acceleration then, the 75 kilograms is the up force minus the down force, which is normal minus gravity. So moving up, your apparent weight is 847.5 newtons, right? Constant velocity, you have no acceleration, so if you think mass times acceleration is up minus down, well, 0 then equals normal minus gravity, or our most common case we usually say is that normal and gravity are the same, so the normal force is 735. And again, think of yourself standing on the scale. When you accelerate up, the reading of the scale goes up, right? When you're going at constant speed, it's at a steady pace, a steady rate. And then when you start to slow down, you have a smaller normal force, and that's what this part of the question tells us. Our mass times acceleration is up minus down. This time, I know my acceleration is negative 0.9 because it's downwards, and I'm saying up is positive, right? So rearranging for normal force, then I go 7.75, my mass, times negative 0.9 plus my gravity force is equal to normal. And so the normal is down. And again, that would be the experience exactly on the elevator. So not that I think these questions are that particularly difficult. I just wanted to go through them using the idea of apparent weight and the language of apparent weight. That's all. So that's it for apparent weight.